Hello and welcome to Mutacell, a series in which I am documenting my design and development of a cell simulator. I originally worked on this project a while ago, but since have learned a lot and wanted to restart and actually kind of follow my design. Previously, I spent uh, an embarrassing 4 hours trying to get a compute shaders to work, but in the end, it didn't really function the way that I intended it to. I wanted to have an alpha value that would make it look kind of like a cell instead of a glorified orb bouncing around space. And I also wanted to have some colors on it that were randomly generated. Neither of those worked. And I ended up going back to my old project for a compute shader and adjusting some of the values, and some of my mistakes were embarrassing. But I was eventually able to get it to look kind of like a cell, where, here in a second, the outside of the circle is higher alpha value, so it's really looks like a denser membrane, and then the inside has a lower opacity, kind of look a little bit like a cell. But the RGB still didn't work after a little bit of tweaks. Yay! I have some bubbles bouncing around. So that was what I originally wanted the compute shader to do in the first place, and now that that's finally working, I can get into some more of the fun stuff. So I wanted these bubbles to start bouncing off and influencing each other, and that meant I had to implement a collision system for them. What I ended up doing was finding the distance between each of the bubbles, and if that was less than the radius of the two, that meant that it was colliding with it, and it would then or set the position of itself back to the maximum distance of the radius, and then invert the velocity of it. And that was really easy to say. It took me a lot longer to implement, so I will just shut up and let you guys watch some of my struggling through all this. Okay, that's enough of my suffering. It isn't quite functioning how I intended, but when do these things ever? I'm going to continue working on it in the background, but I eventually commented out the collision because it wasn't looking realistic enough without adding conservation of momentum, but I was also kind of getting bored of watching the bubbles just bounce around and wanted to start thinking about making them fade away. So, hey look, a squirrel. Before I talk about energy, I want to preface this by saying that I am by no means a chemist, and by even less means a microbiologist. So please look into these topics more before taking them as truth. And if I'm wrong about anything, please let me know. I enjoy learning about these things and would like to correct any mistakes I make and improve the simulation. So, the idea of making the bubbles fade away can be as simple as giving each bubble an arbitrary energy value and then subtracting a factor from it each frame. However, I wanted this simulation to be somewhat realistic, so I ended up reading into how actual cells create and burn energy. When you first look up cells and energy, the first thing that'll appear is the lesson that all science courses drill into you at the start of the cell chapter, and that's that mitochondria is the powerhouse of the cell. Which is a fine way to generalize it, but I think a better analogy is that mitochondria is the factory which produces batteries for the cells to use, and in this case the battery is an ATP molecule. But what about cells that do not have a mitochondria, such as prokaryotes? Well, they produce ATP just like any other cell, but they use other means to form it outside of mitochondria. This could be by using light to cause a chemical reaction which excites the molecule's electrons, which is a process very similar to photosynthesis. Or they could also make ATP by breaking down other chemical compounds that are either randomly floating around the particle soup surrounding them, or by consuming other cells for their organic material. These types of cells are called, and I'm gonna try to pronounce this right, chemoheterotrophs. And what they do might sound familiar because a lot of life that we see are actually chemoheterotrophs, where we eat other animals for their organic material and break it down in our stomach acid in order to convert the organic matter into ATP and fuel for ourselves. And if we are able to steal some ATP from the cells without having to convert it ourselves, that's even better. Okay, that's great and all, but how do the cells actually use the ATP then? Well, there are several ways to manage this. The first is by abusing one critical factor about ATP, which is that breaking it down has a negative Gibbs-free energy. Think about glow sticks and hand warming packets. Whenever you break them, they expel energy and will either emit light or heat on demand due to their chemical reactions. This is what it means for a chemical reaction to have a negative Gibbs-free energy. So if an ATP cell were to interact with something within the cell, causing it to decompose, it would expel energy and could catalyze some other chemical reaction. Alternatively, instead of caring about the energy expelled from decomposing an ATP, the cell could use the physical change in the ATP structure. So a large chain of molecules would alter their shape to accommodate the newly decomposed ATP, which is called ADP, just to make it confusing. This would generate some mechanical energy, and muscles actually work this way, where you have large chains of muscle fibers that physically change shape when interacting with the ATP, clamping down to either contract or stretch the muscle. So that was a long tangent, but what does it actually mean for the simulation? Well, to generalize everything I just said, a cell will collect energy from its surroundings and store it as ATP, which for now I'll just make a random variable called energy, and to keep it simple, since I haven't implemented any way for the cell to actually collect energy, I'll just set it to 1,000. From there, any action the cell performs, like movement or using any future organelles, will cause the energy to decrease. Wait, this is just giving each bubble an arbitrary energy value and then subtracting a factor from it each frame. Oh well, I guess I at least learned some stuff by looking into this. So that was a lot of explanation about how the cells actually work. I'll just shut up for a little bit and let the pretty colors of the actual final result play out for a little bit. Alright, so that was getting the computator to do a lot of what I originally wanted it to do. If you were looking in the background throughout my explanation on ATP and cells, you would have seen me struggling through understanding how to pull the buffer from the computator, adjust some values, and then send it back. Throughout all of my time trying to figure out how to do that, every comment under the explanation was, hey, you can do this, but it is probably the worst thing you can do for a computator because you are forcing the GPU to sync up with the CPU and the world's gonna blow up if you do it or something. I'm not entirely sure. Since then, I have looked into how particle generators work, and I think I'm going to slightly modify my code so that way rather than using pulling down the buffer, I will predefine some number of cells that can exist at a single time and then do it that way. But that's a problem for next time. So if you did manage to sit through all this, thank you. I do want to say that I have a full-time job, and all of this effort that you see now has been an entire week's worth of my time after my job. So expect things to be a little bit slower in the future because I just as the project grows, I'm going to have to spend more time to have a tangible result, so it might take me longer to actually get things out. So if you do want to keep up with my progress, it might be easier to subscribe, so that way YouTube will tell you whenever I post something, because I really don't know when the next video will be. It is entirely dependent on when I feel like I would have a good enough product. So thank you. Hope you enjoyed.